We have over 500 cases. We're averaging 50 cases a day and climbing. So I'm thinking, I have no idea. Like, I think if the rest of the week plays out, we might cancel class. I don't know. Or I guess in-person class, but we'll see. I don't know like what their criteria for that is, because like I think all of the propagation is not happening on campus, right? Like on campus is,
Well, it feels
rules are being followed, right?
yeah. From what I've seen, a lot of students, as soon as they take like one step off of campus, they take off the mask right away.
Mask is off, and you know,
When they're doing on campus,
Yeah.
like right before they get to campus.
They said they disciplined 15 students who like.
yeah, they
I was like, wow, they suspended them.
students and whatever. So I don't know. I wonder if they pause in-person classes and it would just send a signal of how serious they were, even if it doesn't actually. Just like, hey, so we really need this.
My sister's a nursing student, and she said that if the hospitals say that they can't come for clinicals anymore, that will delay her graduation 8 months.
Okay.
She can't. They can't graduate the nursing students if they haven't gone to clinical.
They haven't gone and done that.
And so I don't think that's intrinsically tied to whether or not we go online. But she's like, really worried that
Yeah, so we know that's gonna happen. Sure.
it would suck.
Yeah, I think there's all sorts of like, I mean, already because of why we're doing what we're doing, there's all sorts of consequences, right? Like, I mean, I think we're gonna have our career fair next week, right? But nobody's coming to campus, so how's that gonna play out? You know, I mean, I don't know how jobs are gonna work, you know, this year. Anyway, I've talked to a couple of recruiters and they're like, oh, yeah, we're not hiring this year. We'll come, you know, chat with students on Zoom, but you know, good luck. It's like, oh, not the best year for trying to get a job. But yeah, so if we go online, one option is to continue to do what we're doing, and ChEn, you hop on there on Zoom. We can do this live, or we can try a pre-recorded, and then we can do like live Zoom office hours just at regular class time. So maybe I haven't decided exactly what we do, but I'll maybe ask for your opinion next time, so you think about it, which would make a difference. I assume that it's a little bit of a pain to do the live lecture. It's 9 a.m., you gotta get up and wake up, but maybe as graduate students, you're already here and you're used to that, so that's good. It's probably a little easier for me, and it makes the lecture a little more interactive, but if I do it pre-recorded, it might be a little bit shorter of a lecture to watch. You can watch it at 1.5 speed, and then you can come to class and on the office hour time, and we can chat. Anyway, so we have one on Zoom today. Who's on Zoom? We're missing. Oh, the other Zach. It's been a bad week for Zachs. All right. Well, I guess Zach, if you're on Zoom, I assume you are. I miss you, and feel free to ask a question on chat, and ChEn, you will try and monitor that, right? Okay. She's nodding. So okay. All right. Well, let's have opening prayer. We don't have a volunteer who's willing to give us one. Start off our day. Everybody jump at once. Right.
Our dear Heavenly Father, we're thankful that we can be here at school today. We're thankful that that all of us are feeling healthy. We ask you to continue to protect us and help us to be able to learn. In the name of Jesus Christ, amen.
Amen. All right. So today we're doing shell balances, another day of shell balances. This is our last day of shell balances for a little while. We're going to do shell balances, and then we're going to jump into full differential balances. We're going to talk more about vectors and tensors for a couple of days. then we're gonna do the full balances, and then we're gonna have an exam, and then we're gonna go back and do some mass transfer stuff related to this. I don't know exactly why the course is organized this way. I tried to rearrange it at the beginning of class. I think I've told you this. At the beginning of class, I sat down for like a month and like tried to figure out a new organization. And there's enough stuff that I didn't know in some of the things that I was like, I tried to like reorganize all the concepts in the class and put it in a way that made more sense to me. And I got into this like, like it was a week and a half before class. And I was like, I just don't know enough about these other little pieces. I'm gonna have to do it the whole way through. So I decided to just copy the old organization. And the problem with that is sometimes it doesn't make sense to me why it's organized this way, which is why I tried to reorganize the other time. So anyway, so we're all kind of guinea pigs in this. Sorry if sometimes there's a lecture that sort of feels out of place. Sometimes it feels out of place to me too, but I'll try and orient us. Like one of the things is like vectors and tensors, right? Like we've been kind of using those for a while now, and now we're gonna go back and have 2 lectures on them. But maybe that's good, I don't know. Sometimes you remind yourself and then you study it in a little more depth. So maybe that's better, I don't know. But apologize if it feels a little discombobulated. So, okay, so today we're gonna do shell balances. We're gonna do a quick overview, and then we're gonna just try and do as many examples as we can do for the rest of class time. Go through a couple of these. Hopefully we'll be able to get through them all, but if not, I'll post the rest of the example I didn't get to on the web, and that way you'll have another something. Okay, so overview of shell energy balances. So just like we did the balance equation for momentum, okay, we can do the same procedure and do an energy balance for energy. And I think energy is actually the easiest of the 3 because it's not, like I've said this before, it's not a vector quantity. You don't have to worry about which component of the momentum, right? So in this case, it's just energy. There's only one component to it. And then it's not a mixture like in mass, so that makes our life a little easier here too. Okay. And so we had a procedure for this. So I'm just gonna put that up. Recall our procedure. You don't really need to memorize this. Hopefully you can just remember to do the procedure, but I'm just sort of writing it out in a way to help us think about it. So first you ID the geometry and the direction of transport. Okay, and then, so that was the case, right, where we did our cylinder before. We had to identify which way momentum transport was. Similar thing here. And number 2, we're going to write a balance equation. Right, and so in this case, we're going to have 0 is equal to the sum of the inputs of the energy flow in. Oops. Minus the outputs of the energy flow, and then plus any generation terms. Okay, we'll see some examples of some generation hopefully today. In step 3, we're going to take the limit as the thickness of that shell that we draw goes to 0. Okay, and there's something else I sort of was thinking that we did, but maybe I didn't write in my steps, but we substitute the flux expression in here too. Substitute the flux expression. So in this case, we'll talk about this, but that's going to be the E vector. Okay, and this procedure gives us, an ODE boundary value problem. Okay, so that's our first 3 steps. Again, mirroring what we did with momentum, right? And the 4th step, now we find our boundary conditions. Okay, and then in the 5th step is math, and there we solve the ODE boundary value problem. Okay, so there's sort of the 5 steps. And so again, remember that the key idea from this first part of the course is that we have these relationships for the fluxes right, that go with gradients of things, in this case, gradients of temperature to energy flux. And we're combining that with a balance, and that's what leads to our transport equations. Then we can solve for the temperature distribution, and then we can calculate stuff we want from there. Okay, so that's the process. All right. I'll write this one more thing up and then I'll take any questions. Okay, so let's just remember to then recall our combined energy flux vector. Combined energy flux vector. And this had the symbol E, and there was a convective term, 1/2 rho V squared plus rho U hat plus rho V hat multiplied by the velocity plus pi dotted with the velocity plus Q. Okay, so that was the combined energy flux vector. And we had a way to rewrite it. So we could write it two different ways. One had the internal energy, and one had the enthalpy. So I'll write the enthalpy version up because that one's pretty useful. So this is rho H hat plus P equals rho phi multiplied by the velocity. And then instead of the pi here, instead of the combined energy flux vector, the P comes out and you end up with a tau. V plus Q. Okay. So the terms in here, so this was the convective part. This came from work, right? That was a work term. This was the heat flux, okay? And so this one is the kinetic energy. This one was the internal energy or the internal enthalpy. And then this one is the potential energy to do with height changes, right? And then this is going to give us viscous dissipation. So this is work we're doing on the fluid by mixing, okay? And then this is the heat flux, which was Fourier's law minus K rad temperature. Okay, so hopefully that reminds us. I'll give you a second to write that down as I see the big writing. Any questions about that overview?
There's a question here.
Yes. We got an online question. It's our first one. What's up?
What was the difference between the two equations again?
The difference between the two? Yeah, so the difference is just that there's a pressure in here, right? And so remember pi is equal to, what is it? P delta plus tau, right? So we pulled out the P and V and put that over here, and then that combined with U and gave us H instead, right? So now instead we can have enthalpy flowing in and out of our system, right, instead of internal energy, and we account for that there and account for just the tau here, right? So that's the difference. Does that make sense? That's Zach asking it, right?
He's nodding.
He's nodding. Oh, he's nodding. Hey, I can't see nodding. I need like a Zoom screen on the back wall with like, it's like the NBA games where it's like the online fans, you know, with their weird heads and anyway, that's kind of funky. But okay, so let's do number 2 then, which is first example, conduction in a solid. This one is so simple. Luke doesn't even do it, but I thought it helped us so that we didn't have to do quite so much work on 3 and 4. So we're going to start with this one. There's kind of this like challenge in transport in that there's many analogies. So for instance, we could have done a problem where we did electrical heating in a wire. And that problem is exactly the same as pipe fit. So you get a quadratic, parabolic profile, right, of the heat distribution in the wire. And so you can do these problems where you repeat the problems, right, and then you see the analogies, right? That's useful. It sort of makes you feel happy that everything's kind of the same. Or you can do alternate problems where you highlight differences, right? And then you like, oh, I see how, so then there's this kind of challenge of, as I'm thinking about teaching it, like, oh, do I show them how much it's the same? And we see, or do I show them how much it's different? So today we're doing something that's a little bit different, but a lot of these same things also come out in fluid flow. We just didn't happen to particularly highlight these examples in that case. So, hint, maybe those are things that are useful to ask on exams, right? Like if there's an analogy from one that applies in the other, right? I haven't written the exam, but those are the kind of exam problems you sometimes think about writing. Like, oh, I did this problem in energy, I could do the equivalent problem in fluid flow, and they should be able to get it, right? And that's kind of an easy thing to think of. And now you guys are like smart, savvy students. You're like writing that down, like, oh, exam idea, you'll probably do this. And you realize, when I tell this to the sophomores in like numerical tools class I teach, they look at you like, why are you telling us this? I'm like, because if you think about it and then study, right, I'm telling you what I'm probably going to do for the exam. Yeah. I remember realizing this. I went and I took a electrical engineering, it was a computer science class when I was a graduate student. And I had to do a lot of programming and I felt kind of uncomfortable. So I went and took a junior level, maybe it was even sophomore for some of the students, data structures and algorithms class. And I remember sitting in the class, like being kind of nervous that it was going to be hard. And it was so easy. And it was so easy because, sophomore or junior level classes, like by the time you're a second year grad student, like, they're going slow, right? And the professor's giving them all these hints like this. And the students are dumb and they're just, not paying attention. You're like, he's giving away the secrets, like that's the exam answer. He just told you that's number 6 or whatever, right? And they're like, this class is so hard. Oh, you guys are dumb. I'm sure they got a lot smarter by the time they got to where I was, but at the time I just remember thinking, oh. Then I think the most I took away from that class is like, I can program. If those guys in that class can program, I can program. This is fine. Okay. Maybe I shouldn't say stuff like that. You guys will think bad about me. Dr. Tree thinks everyone's dumb. My graduate students know this. ChEn is like, your favorite word's idiot. Sometimes I don't say that a lot. So
Always.
only reviewers, right? Come on, those idiots. All my papers are wonderful. I don't know that they don't recognize this. I think they've got a problem. Yeah. Okay. So, all right. So our example here, we're gonna assume we've got some solid on top, some solid on bottom, and some solid in the middle. Okay. Assuming solid, so we can get rid of the velocity vectors for now. All right. And we're just gonna do something really simple. I think you probably already know what the distribution is, but we're gonna have T1 temperature, constant temperature on top. T0 constant temperature on bottom, all right? And we're going to look at the temperature distribution in between that slide, okay? So simple conduction problem, all right? And this is just a Cartesian coordinates, right? So previously, in the last example, we did cylindrical coordinates, okay? We can do something similar in spherical coordinates. We'll see if we have a problem on that for the exam. I'm sure we'll see one in spherical coordinates, okay? And right, so in this case, our shell's just this little rectangular slab. You can think of it as having direction into the board. So it's, a rectangle there. But the thickness is just this little strip here, right, of thickness delta y, okay? And then it's, we might have, some distance here that's W and some distance into the board that's L. So the area of these sheets is LW. Okay, and so, this is number 1 here, right? Setting up our geometry. Number 2 is to write a balance equation. And the balance equation is really quite simple, okay? Maybe you can guess it from what I've got here. So the N is going to be along the top, right? And so I'm going to call that EY, okay? Because I only want the Y component of the energy. Evaluated at y plus delta y, okay? So I'm going to call this y and that y plus delta y on those faces, multiplied by LW. So that's the energy flux at a certain point, y plus delta y, multiplied by the area, okay, which is an energy flow. So that's the energy in. Out, I can have something similar. I'm going to have EY evaluated at y, okay? That'll be at the bottom. That's coming out. And now I also have that multiplied by LW. All right? And then there's no generation terms. So when I put that together, I'm just going to write it up here so I don't have to go erase everything just for this little bit. I have EY at y plus delta y minus, I forgot the LW. Now I do have to walk down here. You don't have to catch that, Jimmy. I'm coming back. Her camera works. LW minus EY at y multiplied by LW equals 0. Okay? So in minus out, that's pretty simple balance, right? So remember what we did last time? Who can tell me what the next step is? What do you think, Tyler? Do you remember the next step?
Take that and make it a thinner and thinner slice as it
Right, we're gonna make it a
zero.
thinner slice, but we want this to like become a derivative somehow, right? So I have to divide by something first. What should I divide by? Anybody help him out? What do you think, Dan?
LW and then delta Y.
LW and delta y, that's right. So if I divide that whole thing, I'm allowed to do that on both sides, right? Because there's a 0. I can divide by whatever I want as long as it's not also 0. Okay. LW delta y. So notice that that's the volume of the shell. I think that's always the case. I'd have to go back and look at the other one. But if I remember right, that was the case. So you divide by the volume of the shell. Okay. So now this is going to lead me to step 3. I'm going to erase here and do step 3 on this other side. But that's sort of the end of step 2. Where I might balance equation. Okay, so step 3, take the limit as delta y goes to 0, and then I'm going to plug in EY, okay, the parts of EY that I just erased. So that's what we're going to do, okay? So I take the limit. Do I get a positive derivative or a negative derivative of EY?
That way it'd be negative, but
It's positive, actually. Remember the definition? Not to jump on you. Okay, remember the definition of a derivative? dy, right? F of y plus delta y minus f of y divided by delta y. Guess I forgot the limit right there. Remember that from calculus class? Okay, so the delta in front, that means it's positive. Okay, so that's what I'm going to get. Okay, so that's a pretty simple balance, right? That says that the y direction, the flux is a constant. I could integrate that right now if I wanted, but I think it's easiest to turn it all into a ODE boundary value problem. I think that's the easiest way to sort of systematically do it. Okay, so now we need to plug in EY. So remember EY we had, we'll write out what EY is. So EY is equal to, we just erased this, but we'll just write the y component, 1/2 rho v squared plus rho h plus rho phi. And there's a velocity vector that sits there, so that becomes a Vy. And then this is tau, if I remember right, it's tau, and we need just the y component of tau, right? And then that gets, there's another piece here. So I'm just going to write I and then vi, okay? So this is still like a dot product, but we only take the first component. So this is like tau y, with another vector dotted with v. That's another way to maybe write that, right? So we're of the tau vector or the tau matrix, that looks like this. Tau xx, tau xy, tau xz, tau yx, tau yy, tau yz, tau zx, zy, zz. Okay, I'm taking the row of tau y's. So I'm taking this row right there. Okay, that's what that part is. Okay, and then to that I have qy, and qy is going to be minus k dt dy, which is the y part of that gradient. Does that make sense? What do you think, Mark, with the red Mark Swaneveld? Yeah. Okay, I almost got it first time. I was trying to pronounce ChEn's name yesterday. She got really upset at me. She said it sounded like I was saying it when her mother got mad at her and yelled at her. Sorry, I don't know tonality in Chinese, but anyway, now she's embarrassed. What do you think, Mark? Does that make sense? Is it too small? Am I writing too small today?
No, I can see it.
Okay. All right, so we're going to plug that in. So which terms survive here out of this guy? What do you think? Let's see, Christina, does this one survive?
No,
No. Why?
there is no velocity.
No velocity, right? As a matter of fact, there's a velocity there, so none of these guys go in it, right? That was a waste of handwriting. Okay. How about Brian? Does this one survive? That one survives?
Because there is a velocity in that one.
There is a velocity, but a velocity is 0. Right.
So it does not
So it does not survive. That's right. Okay. But this one, Zach, does survive. Okay. That's the only one that's going to stay. So now we're going to put that one in there. The y derivative minus k dt dy equals 0. Okay. That one's simple enough. Differential equation, even I can do it. Okay, just the second derivative of y equals 0. Right, k cancels out because I have a 0 and I can just pull out the minus sign also. Okay, so that's 3. That's going to be our boundary value problem. We need boundary conditions. That's 4. Who can tell me the boundary conditions? What do you think, Mark?
Temperature at the boundaries is constant.
The temperatures at the boundaries are constant, right? So I'm going to have temperature, and I said it was H, right? So I'm going to have temperature at y equals H is equal to T1. Temperature at y equals 0 is going to be equal to T0. And I've sort of implicitly assumed here, I don't think it's essential, but I've assumed that T1 is greater than T0. When I did my in and out, I assumed that. I think it works out either way, but we'll just say that without a loss of generality, okay? So let's see, we moved on that. While we're talking about boundary conditions, let's just highlight a few others that could have happened, okay? To sort of remind ourselves for energy, what might go on. So that's this system. What others could there be? Okay, so this is an example of constant temperature, right? We could also have constant flux conditions, right? So that would be the case where we have something like Qy is equal to a constant, okay? So these constant temperature cases are something like, maybe really fast heat transfer. Okay, so they're isothermal on the boundaries. These ones are either, one case that they are is if C is equal to 0, they're adiabatic. Right? So that would be an insulating condition, right? So if you put insulation on the top and bottom, now that's going on, okay? Or you can sometimes have, continuous, you have to say that the flux into one side has to be the same as the flux out of the other, okay? You can't have heat piling up at a boundary, all right? So that can be the other case. Another example is similar to what we had last time. You can have symmetry or anti-symmetry condition. Okay, so recall that was when I said that the temperature derivative was equal to 0, or I said the temperature was equal to 0 at a point. Was it 0? Is that right? I think that was right. Now that I'm thinking about it. At a given point, right, as I got even or odd reflection across that point. Another case was boundedness, right? That's a common one, especially in coordinate systems where I've got an R, right? So I have the center. So when I have spherical or cylindrical coordinates, that often pops up. Okay, so this might be the temperature has to be less than infinity, or the temperature derivative might have to be bounded. Okay, and then another case that arises particularly in energy systems is people use this Robin condition, which is let's see, all right, it's of convection. Do you guys know this notation of Dirichlet, Neumann, and Robin conditions? Have you heard that before? I'm not seeing nodding. Some yes, some no. So Dirichlet condition is, and when you talk about PDEs, you're talking about boundary values, that's a constant number. So this is the Dirichlet condition here, constant temperature. A Neumann condition is a condition on the derivative. Okay, so that would be like this condition or this condition here would be a Neumann condition. Okay, and then a Robin condition is a condition that's both mixed together. Yet another example of like Robin, managed to swoop in here and get his name on something where two other people had already had names. I don't know. Dirichlet, I don't know how you get named for a condition that's really obvious. Like Dirichlet, he got like really the constant temperature, condition. Like he got a whole name after that. Like that seems like not a hard innovation. But anyway, so the convection condition here is the heat transfer coefficient times T minus say some external temperature. Okay. And so you've got a derivative here and the temperature that's involved, right? So it's a linear combination of both of those. You can also write this is the same thing, but it's just a rewriting, Qy over H plus T external, okay? So you can write it as the condition for the derivative, or you can write it as a condition for the temperature, but they involve both. This one is kind of nice because you can see what happens if the heat transfer coefficient, so if you're thinking about I have, some real boundary with some fluid or air or whatever, if the heat transfer coefficient goes to infinity, then I get a constant temperature condition, okay? That's kind of useful, right? If you write it in this way, you can see that if the heat transfer coefficient goes to 0, then I get a constant flux condition that has to be 0. I have my adiabatic condition. So that's kind of nice to see how that comes out of that combined condition. This allows you to kind of mix it up and do something in between. Okay. All right, so that's kind of a long detour into boundary conditions to apply the most simple ones to the most simple problem we can come up with. And so we're sort of at step 5, which is the math step, which is, integrate and apply boundary conditions. So who can tell me, if you've done that one in your head or on your paper yet, who can tell me the solution, the general solution to the temperature, our second order differential equation? Who knows that one? This is where I give like the big candy bar. You got nobody. Andrew, I don't think I picked on you yet. Okay. Can you do that one? All right. Take 30 seconds, do it on your paper. Integrate twice. Christina's got it. She knows. You can help Andrew if he gets stuck. He won't get stuck, but you can help him. We're applying the boundary conditions too. Oh, Christina, you're jumping ahead. All right, you got what we got out of it, Andrew?
So isn't it just like delta T on the left side equals C1T plus C2?
Yeah, so T is going to equal C1, or C, Y, C1 Y.
Oh, right.
Yeah, I was like T equals T, right? Yeah, yep, T is C1Y plus C2, right? So when we apply the boundary conditions, we do the one at 0 is our easiest, right? T at Y equals 0 is equal to T0. Well, when I put in 0 there, it's going to give me C2. So C2 pops out real quick. I apply T at Y equals H, I get T1, excuse me, which is C1 multiplied by H plus C2. Well, I know C2 is T0, right? So I get C1 is equal to T1 minus T0 multiplied by H. That makes sense. That's a slope, right? So this is just an equation for a line. I get T is equal to T1 minus T0 divided by H multiplied by Y plus 0. Okay, and that was the one I did the very first day in class, and I said, let's do a little thought experiment, right? Temperature in a solid or whatever, or the day, maybe not the first day in class, the day I did energy, one of the first days, right? I said, oh, we have something linear. We can define a conductivity, right? And this is the same problem, right? Just get a linear case here. Okay, so the same procedure, even though this was a really simple example, same procedure applies to all these problems. All right. So I think I only have time to do one more example, okay? And I'm going to skip example 3 of the composite because it's kind of interesting, but it's in your book. Both of them are in your book, actually, but I think it's a little more involved, and I don't think it's as interesting as the example 4. So I'm going to skip example 4. Section 4. Okay, so we're gonna come over here or do this here. So I'm gonna you can start drawing that geometry again if you want. I'll alter it just a little bit. Take the shell out just again. All right, we're going to have the same system, okay? The same parallel plate setup. But what I'm going to do this time is I'm going to have the top plate move with the velocity u. And I'm going to make this inside, instead of a solid, it's going to be a fluid. Okay? So you can think this parallel plate shearing. Okay? And in this case, we could go through and do a momentum balance really similar to what we just did with that energy balance, but we're going to get out a velocity in the x direction that is uy divided by h, right? That's our linear velocity profile that comes from that shear, right? Okay, so what we want to know is now if I have a fluid and it's moving, how is that going to affect my temperature distribution, okay, when I'm heating this? Okay, and in particular, what we're going to see is that there's going to be viscous heating here. This is fascinating. If there's a large enough temperature, if there's large enough velocity gradient, okay, we're going to get viscous heating that's going to affect our temperature. Right? So we can do a shell balance now. So steps 1 and steps 2, okay, are exactly the same. All right, so I draw, my shell in here, E in, E out, right? Look at the same thing. And those same things give me that the derivative with respect to y of EY is equal to 0. Okay, so that's what I get out of that step 1 and 2. Exactly the same as what we did. Not going to repeat it here because we don't want to put our own selves to sleep. Okay, if I fall asleep giving the lecture at okay. So we're going to skip straight to step 3, which is where we took the limit. So we already took the limit there, but we're going to, so we take the limit. We're happy with that one, okay? But we need to substitute. Yeah, I'm struggling today with the word. Substitute. EY, okay? And so we'll write it up here again real quick. EY at 1/2 rho v squared plus rho h plus rho v hat vy plus, and like tau y dotted with velocity, or that guy we talked about, and then q vector, qy. Okay? So now here's the trick on this one. Question is, which one of these are 0 and not 0? Okay, so let's see. I'm going to pick on Roya. I don't think I picked on you yet. I skipped the front row. I don't know. I just assume you're all paying attention, right? Roya, how about these terms here? 0 or non-zero? 0? Why are they 0?
We have velocity in y.
That's right. Exactly right. There's no Vy, right? That one's 0. So it doesn't matter if any of these evaluate to anything, right? There's no velocity carrying them in or out in that direction. Okay? Let's see. What about this one? Our scary one. Be nervous about that. Dot product makes us a little weak in the knees. What do you think, Tyler?
Well, there is velocity in the x direction.
There is a velocity in the x direction. So the velocity vector, remember this tau y looked something like tau yx, tau yy, tau yz, dotted with v, which is going to be 0, or no, excuse me, vx, 0, 0. Right? So the thing that'll survive is going to be a tau yx times vx. So there will be one there, tau yx, vx. Okay? And then qy is going to be minus k dt dy. Okay, so those guys are going to survive. So let's put them in here. Let's see. Back in my notes. I'm not sure I don't screw it up. I think I have good notes for this. Let me just thread it. I have y derivative, and I'm going to have tau yx vx minus k dt dy equals 0. Okay, so I need tau yx. Well, that's okay. I can get tau yx. I have the constitutive law for that one for Newtonian fluid, right? Right, minus mu e vx dy. Okay, remember that y is the direction of the transport, x is the component, so I remember that that has to be vx, which makes me feel good, right? Because that's the one that's changing. That's the only one that's not 0. So that's another way to double check and make sure that's right. Okay, so now I can rewrite this guy. I'll come over here. D dy of, and then I get minus mu, and I have a Vx from this part, and I'll write the derivative after dVx dy minus k dt dy. Right? Okay, so one thing maybe you've noticed, I'm playing a little fast and loose with my partial derivatives and total derivatives when I'm writing them. Apologize for that. It doesn't matter here because we're in a 1D system, so all my y derivatives can be total derivatives. So I can just rewrite this. I just noticed that I'm writing these as partials out of habit because when we deal with other systems, okay, now I wrote this one as a total derivative. But in this case, they can just be total derivatives. So apologize if that notational thing was throwing off. Okay, so now I can carry through my derivative. I'm going to cancel out the sign. Okay. Oh, one more thing before I do that. Okay, I know this velocity already, right? I don't have to solve that problem. I know that Vx is equal to uy over h, right? And I know that then that dVx dy is equal to u over h. That makes my life easier when I want to do this, right? So I'm going to substitute that one in. Y minus mu Vx is uy over h multiplied by u over h, okay, minus k t dy equals 0. I'm going to get rid of the minus signs because they're bugging me. Okay, make them plus signs. And I'm going to now I'm going to take these derivatives. So I get u over h squared, mu u over h squared. And the derivative of a y, there's just 1, so that's easy. Plus k, second derivative of y. Okay, so now I can rewrite this. Second derivative of y is equal to minus mu over k u over h squared. Okay, so that looks pretty similar to our problem from before. Okay, I've got a second derivative, and now the second derivative is equal to a constant. Okay, this is a source term, right? So I added some source of temperature, some source of heat, right, inside the system. So that's what viscous heating is doing, right? And you can see what matters, okay? It matters what the viscosity is, and it matters what the what the velocity gradient is, right? So if I have a really high velocity gradient, really high viscosity, then this term is going to matter. If not, it's not going to be that important, right? So if I'm sharing a fluid and I'm doing something like a lubrication application, right, where I'm in like an engine and I've got a viscous oil and I'm rubbing these two things together and there's a really small gap, right? Viscous heating is going to matter, right? That oil is going to heat up, right? But if I'm in like an ocean, you know, it's not going to matter much if the gradients are really big. Okay, so on step 4 now, we have boundary conditions. These ones are pretty easy, right? They're just the same as before, the same as we had last time. We have t at h is equal to t1, and t at 0 is equal to t0. Okay, so the only thing we have left then is 5, solve the boundary value problem. Okay, you get a nice clean answer to put on our homework or whatever it is, right? Plug into the computer, whatever it is we're going to do with it at the end. So to do that, we need to take our boundary conditions and our boundary value problem, right? We need to solve the boundary value problem, use boundary conditions to evaluate the constant. Okay, so we've got just a few minutes left, so I don't want to bore you with that. I think you can do this, okay? I'll just tell you, right? When I do this, I take those integrals. Before I had this equal to 0, okay, and so I got a line. When this equals a constant, I now have a parabola, right? Because when I take the integral of that, I get a y there, and I take the integral again, I get a y squared, okay, and I get a parabolic profile. So, all right, sort of an intermediate step. So the answer I'm going to get there is going to be t is equal to minus mu over k, u over h squared, oh, I forgot, y squared over 2 plus c1y plus c2. Okay, c2 is going to equal t0, and t1 that's going to equal this kind of ugly mess. T1 minus T0 plus 1/2 mu over K u squared quantity divided by H. Okay, that's kind of ugly. So you can do some rearranging and get a prettier answer. I'm going to write the prettier answer up here that you can work out. Good night. T1 minus T0 was, let's see, T minus T0 divided by T1 minus T0. So we often use this on dimensionalization and temperatures. Okay, we subtract off the baseline and divide it by the difference. Okay, that is equal to 1/2, and we have a dimensionless number here called the Brinkman number, times y over h by 1 minus y over h plus y over h. Okay, and the Brinkman number is given by the following: mu over, sorry, writing a different thing. Sorry, looked at the wrong line on my notes. Mu u squared over k times t1 minus t. Okay, so a bunch of our constants ended up in there, right? And the Brinkman number, the Brinkman number is big. That tells us that we care about viscous heating. Okay, if it's small, then we don't. You can see that by all the quadratic pieces are multiplied by that Brinkman number. And then I have the linear piece out here, right? So if the Brinkman number is really small, all the stuff that's quadratic goes away, and I end up with just my old linear profile, which is what we did for our first simple problem, right? So if Brinkman, if I have a large velocity, right? I have a big velocity gradient, well, I'm going to end up with a Brinkman number that's big and viscous heating important. Okay. So this is problem of viscous heating. Oh, hopefully that was kind of interesting. I'll put a box right there. Okay, that's all I got, barring any questions. What do you think, Andrew? Makes sense? Kind of a fun example. Okay. Hopefully we'll still see you Friday.
I don't